Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. This podcast is brought to you by Jarhead Diagnostics. Jarhead Diagnostics manufactures in-house diagnostic equipment and storage solutions, as well as distributes for companies like Pico, ATS, and TopDon. One of my favorite tools that I've bought from Brandon and Jarhead Diag is the case for the U-Scope. If you don't have a U-Scope, you probably should, but if you have one, you got to get one of these 3D printed cases, has a magnet on it, has a full-size BNC lead that you can connect to, and it gets rid of the weak point of that scope, which is the mini BNC connection, which is pretty fragile. This case makes this thing nice and secure and makes it an even better tool than it was. So check out jarheaddiag.com. The link is in the show notes. Hey, for listeners of the show, if you want a discount on Jarhead Diagnostic products, use discount code DIAGPODCAST. That's DIAGPODCAST, DIAGPODCAST, for 10% off purchases from jarheaddiag.com. I am happy to have Automotive Seminars as a sponsor for the show. Now, if you're not familiar, Automotive Seminars is a diagnostic technician training company. They've got a website that there'll be a link to in the show notes. And what they offer is top-notch training to technicians like us in the field. I've been taking their training courses for years and have got a ton of benefit out of it. They've got top-notch instructors, John Thornton, Scott Schotten, Scott Manna, and every other month they've got a 2-night course that you can sign up for. Join in, ask questions, and afterwards, you've paid for the course, you can access a recorded version whenever you want. You can rewatch the class 2 years later in case you wanted some details on it, and that is a fantastic feature. So make sure to check out the website to see what courses they have available and what's coming up in the future. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping, and I'll be your host once again for this episode. Thank you for joining me. This week on the show, I'm going to do a bit of a conclusion to one. If you listen to the episode with Ben Varnado, at the beginning of the episode, I was talking about a 2015 Infiniti Q50 that I was having some lean codes and kind of ran out of tests in my initial visit to the shop. I did end up getting this one fixed, so I wanted to go through that with everybody. So if you listen to that episode, you know a little bit about this car. I'm going to go over some of those details again. So a little bit of a review, but I will give some more detail on the specifics so that you have all the information. The case studies that I've been sharing recently and that I want to continue to share more of are vehicles that I struggle on because there's plenty of those. But I think it's really important to get that information out there. Not only what the fix for the vehicle is and helpful tips that might help you get through some of these things, but just sharing that, hey, everybody struggles when we're trying to do this stuff at any level within the field, especially a high level. And if we're trying to work on, all makes and models, it is challenging a lot of the time, and it's not always a quick and easy solution, but there are ways to work through it. There are ways to get to the conclusion. But that's kind of what I want to share with as many case studies as possible. This being one of those, because it was not a quick and easy one for me, at least. But let's go through this. Again, 2015 Infiniti Q50. This is the 3.7 liter naturally aspirated V6 motor. This is not the hybrid version. The shop called me in because they were having lean codes. They identified a P0171, P0174 lean on both banks. They kind of ran through their initial testing and weren't able to come to a definitive answer as far as why it was running lean. According to the customer, this thing was running fine. And then all of a sudden it started running poorly and the check engine light was on. And the shop noticed the same thing, is occasionally this thing would kind of miss and sputter. Mainly at idle, they were noticing this. And the check engine light's on with the lean codes. They identified positive fuel trims. And again, they went through some of their basic checks. So I was told by the tech the checks that they did is they smoked the intake to check for vacuum leaks. They checked the fuel pressure, and he actually still had a gauge hooked up to this. They teed a gauge in back by the fuel tank, and they had the pressure gauge there with the back seat up. When I got to the vehicle, he did verify that the fuel pressure was adequate according to the specification that he found, which was around 50 pounds of fuel pressure. And that was all times, whether it be idling or going down the road, it maintained adequate fuel pressure. Other than that, said he went over kind of the basic sensors in the scan tool, looked at mass airflow, coolant temperature, intake temperature, air-fuel ratio sensors, that sort of thing, just to see if there's anything out of place. And he wasn't able to identify one thing that'd be causing the entire engine to run lean, right? Because it's both banks and both sides are relatively equal in the amount of positive trims that they have. And this is the information he's telling me. Of course, I want to verify all that. So I get the keys, check out the car, verified everything that he was telling me, and it was all right on the money. Fuel pressure was adequate, both at an idle and under a load. I actually did get a fuel sample because the gauge that was teed in has a little relief valve. And I've said it on the pod before, if you're checking pressure, just get a sample. I've made that part of my routine for any vehicle. I'm taking a fuel sample if I'm checking if I'm going that far, right? And this guy kind of already did it for me, which was nice. But if I've got a gauge on there, I'm getting a fuel sample, especially if I'm chasing a lean condition. But there's been a ton of cases where I've had really strange things go on with the fuel, whether it be water, ethanol, E85, or some sort of, just weird contamination. I had one that looked like mud. I don't even know what was in there, but it sure wasn't fuel. I had a Kia with E30 that made it run really, really weird. I should say not weird, but when it was lean and when it was not lean was very odd on this Kia. And it was E30 that was in there, not E85 and not the E10 to 15 that's normal pump gas, but E30 was enough to throw this non-flex fuel Kia off. So anyways, I get a fuel sample from this thing and it's just normal pump gas. And as far as I can tell, this Infiniti is not a flex fuel vehicle anyways. There's no percentage for ethanol content that I could find in the scan tool, or usually I'll check back by the gas tank and the filler neck, and I'll see if it even indicates that it's a flex fuel vehicle or not. And this one didn't appear to be one. So, and the gas was normal pump gas, which with about 10% ethanol. So that is eliminated. And that's definitely something that can cause your engine to run lean if it's not set up for flex fuel, but you do put E85 in there, but not the case. So I go through scan data and I do find the codes, the P0171, 174 lean for both banks. The trims are elevated in the positive direction, meaning the computer is adding fuel to compensate for a lean condition. It did get into fuel control when the long terms were up between 20 to 30%. Then you could see the short terms bounce, back and forth to zero at that point. And it actually ran pretty well once the trims had compensated and it got into fuel control. Now, what I did find is if I went into the work function area of the scan tool and I reset the trims, which is something I like to do, is just sometimes that can fix a car, right? Like sometimes the fix could be made to a vehicle, and depending on the application and the computer, you need to reset the fuel trims in order to get the engine to run correctly. Otherwise, it may take a while for those trims to reset on their own, and you might think the car's still broken when really it isn't. So I like to do that. And then I also like to see what happens after I reset the trims, right? Maybe it's fixed, but do they bounce right back to where they were? And does it run poorly in that period of time, right? Like after I reset the trims, does this thing actually start to run lean? Which this one did. You could tell it was like sputtering and misfiring as soon as I reset those trims. And then the short terms skyrocket up in the positive direction. And then eventually the long terms will catch up. And then it starts to run okay again. Once it gets into fuel control, it compensates for that lean condition. It's running pretty well. Okay, so as far as I can tell, this thing is actually running lean. Now, my next question is when is it running lean? Now, I'm sitting there in the parking lot, so I know it's at idle, but is it running lean under a load, right? Not just necessarily elevated RPM, but under a load. And this is one thing that can help you pick out a vacuum leak pretty quickly. And you want to either power brake or drive the vehicle in this case, because the load key is the really important part here on a mass airflow sensor vehicle, which this is. And I should actually mention, this is a mass airflow sensor vehicle, but it has 2 mass airflow sensors and 2 throttle bodies, which does make this one a little bit unique, something that I'm not used to. I haven't diagnosed a ton of drivability issues on a dual throttle, dual mass airflow system engine, but that's what this one is. And I'll talk about that more as we go because it kind of threw me off a little bit as far as figuring out what was wrong. But on a mass airflow sensor engine, if you want to quickly identify if you have a vacuum leak, if that's what's causing your lean condition, load the engine up, just power brake it or go drive it and watch your trims at that time under the loaded state versus the idle state. And what you're doing is you're bringing the pressure inside of the intake manifold closer to atmospheric, right? You're putting the engine under load, meaning you're opening the throttle and you're equalizing or bringing it closer to equal pressure, the outside and the inside of the manifold, which then basically gets rid of the vacuum leak, right? A vacuum leak is only there because there's a difference in pressure between the outside, atmospheric pressure, roughly, we'll say 15 PSI on the outside of the manifold, and then all of the pistons pulling against the back of the throttle blade on the inside of the manifold creates that vacuum, the lower pressure than atmospheric. And so atmospheric pressure is going to find its way in through any leaks, right? A blown out gasket, a torn hose, whatever the vacuum leak is, right? But if I load that engine, I am now bringing that pressure on the inside of the manifold by opening the throttle and allowing the engine to run at a higher RPM under a higher load. I'm equalizing those pressures. And so any opening, whatever your vacuum leak isn't necessarily a vacuum leak, right? All the air is going to be going in through the throttle. There's not a difference in pressure. So that leak really isn't a leak anymore. So what I'm getting at there is your trims will now retreat back towards zero if that's the case. Okay. And I do want to make a note here, and I learned this from one of John Thornton's classes a long time ago, so I'll give him credit here, but don't just rev up the engine in park or neutral. If you look at the manifold vacuum, when you do that, you actually increase the manifold vacuum. Let's say I just bring the engine up to like 2 grand in park or neutral. The manifold vacuum will go up, or you could say the pressure would go down. If you're watching a vacuum gauge, you'll go from like 17 inches of vacuum to 20 inches of vacuum when you rev up the engine in park, because what it is a freewheeling engine doesn't require much load to spin faster. And so you get just a little bit of a throttle opening, but now you have that many more intake strokes happening against the back of that throttle, and you actually increase the vacuum. So what I'm getting at there, and what John taught me years ago, was that you are actually amplifying the vacuum leak in that case. You're creating more of a pressure difference between the outside and the inside of the manifold. And so just revving up an engine in park or neutral and a mass airflow sensor engine really isn't going to point out a vacuum leak to you. You need to load it. That's the key. So power brake it or go drive it. Anyways, I did that. It's lean all the time. Okay. So I can say with somewhat confidence that there's not a vacuum leak. There are some other checks we can make. The tech did say they smoked the intake. I try to take information like that with a grain of salt because I want to do it. I want to see it myself because I don't know how is the test done, what was overlooked. There's endless variables. I always like to see the test for myself. I don't take that stuff, in stone. So we're lean all the time. I'm going to go through with my scan tool and I check all the, important sensor data PIDs that could be affecting this. Of course, we're going to look at stuff like engine coolant temperature, air intake temperature, look at the air fuel ratio / oxygen sensors. So it's air fuel ratio sensors on the upstreams on this and their oxygen sensors on the downstream. Make sure that those are all in agreement. And for an engine that is lean on both sides, a V-style engine with 2 banks. And I should say they're both equally lean, right? So the trims are positive in an equal amount between the bank 1 and bank 2. The odds of it being air fuel ratio or oxygen sensor caused, although possible, is probably unlikely because they have to be both failed and both failed in the same way, which again, okay, it could happen, but it's unlikely. But I'll take a look at them, and they're all in agreement. And when I say that, both side to side, but front to rear as well, right? If you have an air fuel ratio sensor that is not reporting properly, it's going to say, hey, it's rich when it isn't rich, or it's lean when it isn't lean. Your downstream sensor is going to tell the truth there, right? So let's say, this is not this car, but let's say air fuel ratio sensor upstream is saying, hey, the engine's really lean. That's what it's reporting. So the engine responds by increasing the fuel trims, adding more pulse width injection to the fuel injector, adding fuel to the engine, right? Now, if that air fuel sensor is not actually reading correctly, and now you're adding fuel to an engine that wasn't running lean, you're going to get a rich condition, right? Who's going to see that? The downstream sensor is going to see that and report that, right? So you can look at the front and rear and see, are they both reporting correctly? Or, there's one lying, essentially, is what I'm looking at there. They all look all right. And again, unlikely that that's the cause of my problem, but I do want to check that out because air fuel ratio sensors are a big input here as far as driving fuel trims. So those look okay. Now I've got 2 other sensors here that are also important to fuel delivery. And these 2 sensors are kind of where I got threw off a little bit and was difficult to make a call. I'll start with mass airflow sensor. Now, again, this has 2 mass airflow sensors, and they each have their own individual data PIDs. And then there is a total grams per second airflow into the engine. Now, I wasn't 100% because it doesn't spell it out. I was like, does it add the 2 together and just make it total? I think that is what it does. Or is it doing some sort of weighted calculation? Is there something else happening? I wasn't 100% sure, but you could see the individual sensor PIDs and you could see the total air volume going into the engine. I should point out the sensor data PIDs were in voltage and the total was in grams per second, right? So you'd have mass airflow or airflow mass into the engine, grams per second, which we're used to seeing, and then it had individual mass airflow sensor data PIDs, okay? What I could tell you on my initial inspection, this thing was about 5 to 5.5 grams per second of air on a hot engine running in gear at idle. All right. And I like to make those checks. And if you've done any mass airflow sensor stuff where you're looking to see, is the sensor skewed? You would look to see, are the grams per second roughly equal to the engine size in liters? Okay. So if it's a 4-liter engine, you would roughly expect 4 grams of air per second at a hot idle in gear. Now, I can also say that this is definitely not true all the time. I'd actually say a lot of the time on newer engines, I found this rule of thumb that I could rely on certain engines to be not true. So I'll still think about it, but I don't take it as, a 100% certainty that there's an issue. Okay. Now, this is a case too where I'm not going to weight this too heavily because 5.5 is definitely more than the 3.7 that the engine is. But even if that was wrong, it's wrong in the wrong direction for the problem that I'm having. Okay, think about it. Let's say there's a 3.7 liter engine and we're reading 5.5 grams per second of air. If that was incorrect, it would mean that the engine thought there was more air entering the engine than there actually was. Let's say 3.7 grams per second is normal. It's not on this engine, but let's say it is. It would actually be in a rich condition. Okay, so at this point, I'm assuming that even though this doesn't match up with my old school rule of thumb, that it's not my issue because it's higher than the engine size. Now, could this number still actually be too low? Yeah, it definitely could. But my problem is I don't have a known good. I don't know what normal is on this engine. But that's my reading I have at idle for the mass airflow sensors, right? And again, it's a dual throttle, so that kind of changes things too, right? Of course, there's going to be an ability for more air to go into this engine than a single throttle engine. So I don't know how that's going to play out yet, but that's the data that I observed here at idle. All right, so the other data pid that I looked at, and just these are some of the basic ones that I'm going to peek at when I have a fuel trim issue. The other data pid that I looked at was the MAP sensor. And this definitely threw me off a little bit, so I want to share this with everybody. This was reading on the scan tool data pids 2 kPa. And for reference, 2 kPa or kilopascals is 0.3 psi, or it's 1/2 of an inch of mercury. Okay, so that's almost nothing. And it's definitely not right on a running engine at idle. It also never changed. I could rev up the engine, I could do everything, and that value from that MAP sensor never changed, which I thought was very, very strange. Now, I didn't have a code, right? You should have a P0106 for MAP sensor performance or something like that, but it's definitely not right as far as what I'm used to seeing. And I looked, and there actually is a MAP sensor plugged in on the top of the intake manifold, so it's not like it's a data pid for something that doesn't exist on the vehicle, or so I thought. So what I did was I unplugged the sensor and I used my sensor simulator, right? You get this in the ASE wave test kit. You can dial in resistance, you hook it up to the 3 wires, and then you can dial in whatever value you want the computer to see. And what this is proving out is the circuitry to the MAP sensor and the computer's ability to observe the voltage coming out of the sensor and do something with it. Right. And so you can see the value on the scan tool. You could actually see it in inches of mercury, which was helpful. And I just dialed this into where you would see the intake manifold pressure at idle, roughly, right? I put it at about 17 inches of mercury at an idle. That's about what this engine would normally be at. And so my goal here is to see does this fix my fuel trim issue? Okay. Well, it didn't do anything. I reset the trims while I had this on there, and it didn't do anything. And it didn't set any codes pertaining to a MAP sensor, which again, I thought was very strange, but it didn't change anything. So I'm very suspicious of this, but this is a problem. Like, this is very obvious. And again, there's a sensor there on the intake manifold. There's a harness, there's a wire. I can change the value. So I was talking in the shop. I was like, well, we should get a sensor for this thing and just let's see what happens, because this is not right. Well, in the process of doing that, we took out the old sensor and we looked at it. It's a dummy sensor, meaning that there are no male pins in the sensor itself, right? It's got a connector that plugs into it. It's got circuitry. The computer responds to it, and the sensor goes into the intake manifold, right? It's exposed to manifold pressure, but there's no pins on it. And this is very confusing, but we came to the conclusion that it's not used on this application, but it must be on others. And fast forward to doing my research for this episode, I didn't know it at the time. The MAP sensor is only used on the hybrid applications. All right, so you can get a Q50 hybrid, which this one is not. That one uses the MAP sensor. So the MAP sensor you get for that has pins on it, and it actually reads the manifold pressure. And the engine computer actually uses the value. For this one, the calibration, the software that this engine computer has, it's basically programmed to ignore it for the non-hybrid version. right? So all I was doing there was absolutely nothing. The computer wasn't observing that voltage, even though I could see it on the scan tool. It's not using that in the fuel calculations. So that was pretty much a big waste of time. Okay. So we're still running lean. And what I'm kind of down to now is my mass airflow sensors. But again, I'm not incredibly sure on what's good or what's bad or how I'm going to prove it on this particular engine. Now, one thing you can do is a VE test, which I've talked about before, and this involves looking at the engine RPM, the air temperature, the grams per second into the engine. You use the engine size, the cylinders, and you put all this into a calculator. I like using the ATG VE calculator. You can just Google it and it's free. You put these numbers in, you get a percentage. And generally speaking, on a naturally aspirated engine, you want to see above 90%. Trouble there is, and you'll see that with this engine, is if we're talking about something older, like you really need to consider what you're working on. If you're talking about something older, like I'm doing a VE test on a 2000 Chevy truck with a 350 in it with a push rod motor, right? 85% on that might be as good as it'll ever be. Okay. And that's how that engine breathed, right? It was not as efficient as a newer engine. I remember when I was teaching in college, we would have the students do VE tests on their car, and they always loved doing that because they could put the accelerator all the way down on a test drive, and that's always fun for everybody. But we had like a 21 Toyota naturally aspirated engine that was at like 110%. And you might say, well, how could an engine breathe more than 100%? Well, there's systems on these engines like variable valve lift and cam timing and things like that, where you can get over that theoretical airflow through an engine because we're essentially changing the engine dimensions as the vehicle's running. And so we get the higher numbers. So on that, 85% is terrible. It's awful, right? But again, I like to see close to 90%. If I see that, I'm usually pretty happy with things. That's what I got from this when I did a VE test, was about 93%. And the other thing I'm looking at is, I looked at the fuel pressure while we're giving it a major load on the engine, and it was able to support the fuel pressure that it needed. I'm trying to feel how is the power on this thing as I'm driving. Felt adequate power to me. Now, granted, I drive a 2010 Ford Transit Connect, so just about anything's going to feel like adequate power to me. And I think I need to take that into account when I'm driving some of these vehicles, but it felt okay to me. I also like to look at the O2 sensors while I'm in a full throttle mode to see, are they going into a rich state? And they were. They were pegging rich, meaning that we're supplying enough fuel for this thing that the O2s are actually going rich, right? It's not starving for fuel as far as I can tell. So the idea of the VE test, for me, it can tell you a number of things about the breathing of an engine. But for me in this situation, I'm looking at it to help me gauge. Normally it would be if the mass airflow sensor, but in this case, are the mass airflow sensors reporting correctly? Right? Are they underreporting? Is that why we have a lean condition? 93%, I don't know that I can necessarily point to them. Now, one other thing I did notice about these two sensors, both at idle and under a load, because I graphed the data on the scan tool, there was one sensor, bank one, I believe it was, it doesn't really matter, but there was one sensor that was reporting slightly less than the opposite sensor at all times, meaning at idle, mid-load, heavy load, it would report less voltage than the other sensor at a given RPM consistently. Now, I didn't know if this was normal. It didn't seem normal, but again, this is one of those little things where I'm not super familiar with these engines, and I don't want to go diving down a rabbit hole if I don't know. Maybe that's just the way this is set up. Maybe the way the manifold is constructed, one side gets a little bit more air in than the other, right? I mean, once the air's into that manifold, it's going to get divided up equally into the cylinders, but does it enter both sides of the engine equally? I don't know that. Okay. So the VE test didn't really show me anything, but I still want to take a physical look at these mass airflow sensors, right? And at this point, I'm just kind of running through everything that I would normally do. I don't have anything really pointing me towards something yet. I thought I did with the map sensor, but that turned out to be nothing. But I still have to keep going with testing and just go through everything that I normally would. So at this point, what I'm going to do is I'm going to pull out these mass airflow sensors and do a visual inspection on them. And not only the sensors, but the air filters themselves. Okay. Because as we all know, the way that the air passes across the sensor can affect its reading. Okay. So I pull the sensors out, which is easy to do. They're very accessible and they actually look really clean, like not dirty at all. Which obviously if they're dirty, that's something that can cause a lean condition, but they looked relatively clean. Now, the other thing I looked at was the air filters themselves. Now, these things were dirty and they were actually kind of collapsed in on both sides. Like they'd been in there for quite some time. I was like, well, maybe this is causing our problem here. This might be it right here. Is just, and there's two different air filters because there's two snorkels going into this intake and they were both aged, both dirty and both slightly deformed. So I did tell the shop, I'm like, hey, we need to put some filters in this thing. That's my next step here. I'm still questioning maybe the mass airflow sensors themselves, but we got to get some filters in this thing and reassess. So they get a couple filters for it. We slap those in there and I reset the trims and it didn't change anything. The numbers that the mass airflow sensors were reporting were the same. Oh, and I should mention the grams per second at a full load. I hit about 200 grams per second on this engine when I was doing my VE test. And then at idle, again, they were still about 5 to 5.5. We're still lean. We're still positive. Last thing that I wanted to do here, because I was kind of running out of tests at this point, is I wanted to smoke the intake and not necessarily just the intake. Because I went through that whole thing of how I was determining, hey, I don't think we have a vacuum leak here. But I want to smoke both the snorkels and the crankcase all at the same time, right? Because the crankcase has the fresh air breather for the PCV system that goes into the snorkels. That's between the mass airflow sensor and the throttle on both sides. So it's potential if we have a crankcase leak that we could be getting unmetered air into the engine there, right? So that's a possibility. And I gave the snorkels a visual, and I didn't see any cracks, but that doesn't mean there isn't one. So what I did was I capped both air intake ducts, the snorkels, right at the mass airflow sensor. So I would say just past the mass airflow sensors. I put 2 caps in there and then I fed smoke into the intake. And I just want to see, is there leaks anywhere, not only in the intake, but then also in the crankcase and the air ducts? Do we have any sort of chance for like a false air situation to be throwing these numbers at us? So I did that. Perfectly sealed. Actually built up like a little bit of pressure when I would pull off like the dipstick tube or the oil cap. You could see smoke coming out of there. And there was no leaks anywhere. And so the shop that they did the smoke test of the intake, I don't know exactly how they did it, but they were accurate. There's no leaks there. And it confirmed what I was seeing with my scan data. Not a vacuum leak. And now I can say there's not a false air situation here either. So at this point, I'm not entirely confident on what the problem is. I'm leaning towards mass airflow sensor. You know, your gut tells you something. And I'm leaning toward mass airflow sensors, but I wasn't quite 100% convinced. And partly because I didn't know how the computer took in the values for the mass airflow sensors too, right? I did mention there was one that was less than the other one. So is one side failed enough to cause the whole engine to be lean? It's possible, but I don't know that for sure. Is there anything else on this vehicle that I could potentially be missing? That's definitely possible too. And so I told the shop, I'm like, hey, I'm not ready to make a call on this. Let me do some reading, talk to some people, and I'll get back to you on this thing. So with all that, I decided I'll, move on with my day because I spent enough time on this, and I'll talk to some people. And that's where having a network comes in. I know I'm sorry that I say that every single episode, but it is important. And reached out to some friends and got some ideas. And, a lot of it was some of the stuff that I had checked, but some of it wasn't. I had a couple of people reiterate how important mass airflow sensor inputs are for Nissans, Infinitis, and that I should really be focused on that. PJ Walter sent me a TSB that I did not see in my searching that had an update for calibration for P0171 and 174. The updated calibration didn't really pop in my head. I didn't check for it. I should have. I didn't check for it, but the way it was acting didn't seem like a software thing that just decided to change all of a sudden, right? Like when I reset the trims, this thing ran like garbage. And although possible, it just didn't like strike me as a calibration issue. But, I'm like I said, I'm kind of running out of stuff. I want to verify that that's not the case. And also I was kind of thinking after the fact, well, what if somehow we just have the wrong calibration in this thing, right? Somebody put a computer in it, somebody programmed it the wrong way. That's a possibility. And I never did look at the engine calibration to see if it was correct for this vehicle. And then I'm thinking of, what else can this be? Obviously the mass airflow sensors are in question. Maybe it's like an injector situation, but I'm thinking that's kind of unlikely since it's pretty equal. The trims being off are equal side to side. Maybe an ECM software calibration issue. That's possible. But also those mass airflow sensors, right? And because the filters were, again, dirty and old and a little deformed, even though they weren't dirty, I'm really, really thinking those mass airflow sensors. And again, one of the people I talked to is like, those are really important on these Nissans. And I think if it had just been a single mass airflow, I probably would have told them get a mass airflow sensor for it. But I was hesitant because of the two. Like, it just threw me off a little bit. But I called the shop owner the next day. I'm like, hey, will you just order a couple of MAFs for this thing? Get some high quality ones, and I'll come over, we'll install them, and we'll try and we'll see. I was like, this is the most likely thing that is causing your problem, but I'd like to be there and see for myself, if for no other reason, that if it fixes it, I can have some known goods, right, on this particular engine. So he said, yeah, I'm willing to do that. And so I came back the next day when he had them. I put them in myself. So I reset the trims, and immediately they were way better than they were before. So they didn't climb all the way back up. They got up to like about 10% or so. So I went out and drove this thing, got on it. It had a noticeable jump in power from when I drove it the day before. And so this car actually is pretty peppy now that it has the correct amount of airflow being read in the computer. Now, again, it wasn't starving for fuel. The O2s were pegged and it accelerated fine, but now it's noticeably more acceleration for this thing with the correct amount of airflow. After I gave it a few runs, the trims actually came down. I mean, they were like 5 to 8 on the long term, and the short terms were bouncing around 0. And so they were right back to where they should be. So the mass airflow sensors fixed it, and both of them. And I was, again, questioning whether it was one or two of them. But here's the thing. Both of the values were now higher, and they were equal. And that was one of my questions. Was the difference in value a problem? I think they should be equal on this engine. Now, they weren't perfect all the time, but they were real close. And when you sat there at a steady idle, they were almost identical. Now, for known goods here, 7 to 8 grams per second is normal at a hot idle in gear on this thing. Wide open throttle, we're closer to 230 grams per second as opposed to the 200 that I had on my initial runs on these things. So it upped the amount of airflow that the computer was using as a base to add fuel, which is exactly why it was lean, right? I mean, it makes total sense. And I think, a few things, had I had a known good as far as airflow goes on this thing, it would have been easy. Super easy. Next time I get one of these things, it'll be super easy. I'll look at those numbers. I'll compare it to my notes, and I'm like, yeah, it's mass airflow sensor. Make your checks and stuff and make sure it's not a an air leak problem or a filter problem, but once you've verified all that stuff, okay, it's sensor time. And I also know now that they should be the same value between right and left mass airflow sensor. Now, the VE test also came back at over 100% on this engine. Okay, so 93, not good for this engine. Could it be worse? Oh, yeah, definitely, right? It could be starving for fuel, but it wasn't quite that case here. But it needs to be over 100%. And I didn't even really consider it until after the fact, but this engine has variable valve lift. It's got a motor on the top of the cylinder head that kind of operates like the BMW Valvetronics system, where it moves an eccentric shaft to change the depth of the valve opening. And so, of course, that makes sense on how this thing's going to hit over 100% of the theoretical load for a 3.7 liter, because we can essentially change the engine breathing dynamics as we're going down the road. And again, that was kind of one of the points I wanted to make here with the VE test, which is a really powerful tool. It's something, again, where you kind of have to have a known good, or at least take it with a grain of salt and really consider the engine that you're working on. You know, what's good, what's bad, how is it going to point me to the direction that I need to be, right? Mass airflow sensors have always been a little tougher to pinpoint a fault because, as I've mentioned before, they're a sensor where we can't take a physical measurement to verify the accuracy of the sensor. Right, I can't physically measure how much air is going into an engine at a given point. It'd be fantastic if we could. That would, I think me and Brian Mann talked about it. That would be an awesome tool if I could sell something that you strapped on to the air intake of the engine and it actually measured airflow accurately, and you could compare it to what was, you know, on the computer from the mass airflow. Man, that would make things so much easier. But as far as I'm aware, such a thing doesn't exist. But if there is, let me know about it. I'll buy one right now. It's not like other sensors, right? Like coolant temperature sensor. We just measure the temperature of the coolant. Okay. Map sensor. We just measure the manifold pressure, right? There's so many, and you can go on and on like that. Like there's so many sensors where you can tell what if what it's measuring is accurate or not by using another type of physical measurement. We can't do that with mass airflows. So it gets a little tricky as far as, well, how much air is actually going into the engine? How much air is supposed to go into the engine? And that's our tool there to help us out with maths, is known good numbers. So I guess the final thing that I'd point out here is get as many known goods as you can. If you're looking at an engine, you got the scan data up, take a note of what known good for grams per second is at a given point, and then put that in your notes somewhere so that you have that for future reference, because had I had that on this one, it would have made it a lot easier. All right, that's it for today's episode. I hope you found that interesting and helpful. Like to appreciate everybody out there for listening, all the feedback I get on the show. I always appreciate that. But with that all out of the way, let's get out there, start fixing the world one car at a time.